Hello everyone and welcome back to channel. If you have just finished part 1, you now have a solid grasp of number system, the core language of digital electronics. But numbers are just the beginning. How do we actually use those zeros and ones to make computer think? In this video, we are going to dive into the fundamental building blocks of all digital circuits, that is logic gates. We will explore what they are, how they work, and how they connect to form complex circuits. By the end, you will be able to build basic logic circuits yourself and understand their behavior using truth tables. A logic gate is the most basic building block of any digital circuit. It takes one or more inputs and gives a single output based on the specific logic function. You can think it of like an electronic decision maker. And key concepts are binary input and output. It only understands binary data, either high, that is 1, or low, that is 0 signal. This simple on or off state is what all digital systems are built on. Truth table. A truth table is like a complete map for the gate. It lists every possible combination of inputs and shows you exactly what the output will be in each combination. Then coming to Boolean algebra, this is the mathematical equation that represents same behavior as the truth table. It's a compact way to describe the logic function of the gate using algebra. The AND gate. AND gate is one of the most fundamental logic gates. Its job is simple. It only produces high output when all of the inputs are high. Think of it like a strict condition. If you have two inputs A and B, the output will only be on if A is on and B is on. If even one of them is off, the output is off. This is the standard symbol for the two input AND gate. You will see this shape in every digital circuit diagram. The two lines on the left are input AB and the single line on the right is called as output O. The truth table shows us every possible combination of inputs. In the first row, if both A and B are 0, the output is 0, that is low. In the two rows, if either A or B is 0 and the other is 1, the output is still 0 because AND condition isn't met. Finally, in the last row, when both A and B are 1, the output is 1, that is high. This is the only time the gate outputs a high signal. The Boolean expression is the algebraic way to describe this logic. For an AND gate, it's written as y, that is output, is equal to a into b or ab. A dot symbol represents the logic AND operation. So this expression reads y is equal to a and b. The OR gate. OR gate is another fundamental logic gate. It's much more flexible than the AND gate. Its rule is simple. The output is high if any of its inputs are high. The output is only low if all of its inputs are low. Think of it like a choice. The output will be on if either input A is on or input B is on, or if both on. This is the standard symbol for the OR gate. It has a curved shape at the input side and a pointed output. Just like a AND gate, it takes two inputs, A and B, and gives the single output O. Let's look at a truth table. In the first row, if both A and B are 0, the output is 0. This is the only case where the output is low. For all other combination, if at least one input is 1, the output is 1. You can see this in the next three rows. When A is 1, when B is 1, and when both A and B are 1, the output is always 1. The Boolean expression for OR gate is written as A is equal to A plus B. The plus sign represents logical OR operation. So this expression reads Y is equal to A or B. The NOT gate, also known as an inverter, and it is the simplest logic gate. It only has one job. to invert its input. That means it changes a high signal to low signal and low signal to high signal. It is like an opposite button. If you put a 1 in input, you get a 0 as output. If you put a 0 as input, you will get a 1 as output. The NOT gate symbol is a triangle with a small circle at the output. The circle is called as inversion bubble and it also indicates a signal inversion. Let us look at the truth table. It's very simple because there are only two possibilities. When the input A is 0, the output is 1, and when the input A is 1, the output is 0. The Boolean expression for NOT gate is written as y is equal to a bar or y is equal to a apostrophe. The bar or the apostrophe above the variable indicates the logical inversion or complement. The NAND gate. It is a short for not and. It's the exact opposite of an AND gate. Its output is only low when all of its inputs are high. For any other combinations of inputs, the output will be high. The NAND gate symbols look just like the AND gate but with a small circle or inversion bubble on the output. That bubble represent the not part of the gate's name. Coming to the truth table of NAND gate, as you can see, the output for the NAND gate is exact opposite of the AND gate's truth table. The output is 1 for all cases except when both inputs are 1 where the output becomes 0. The Boolean expression for the NAND gate is written as y is equal to a and with b bar. The bar over the expression means not, which inverts the result of AND operation. The NOR gate, which is the derived logic gate. It's short for not or, which means it's the exact opposite of an OR gate. The NOR gate has a simple rule. Its output is high only when all of its inputs are low. For any other input combination, the output is low. The NOR gate symbol looks like the OR gate symbol but with a small circle or inversion bubble on the output. That bubble represents the NOT part of the gate's name. Look at the truth table. When both inputs A and B are 0, the output is 1. This is the only case where the output is high. For all other combinations, if at least one input is a 1, the output is 0. This is the opposite of the OR gate's behavior. The Boolean expression for the NOR gate is written as y is equal to a or b bar. The bar over the expressions means not, which inverts the result of the logical OR operation. The XOR gate, which stands for exclusive OR, has a special rule. Its output is high only when its inputs are different. If the inputs are same, the output is low. Think of it as a logical OR. The output is high if the inputs are different. The output is low if the inputs are same. It's also known as exclusive OR. The XOR gate symbol looks like OR gate symbol but with the extra curved line at the input. This distinguishes it from the regular OR gate. Look at the truth table. When both inputs are 0, the output is 0. When the inputs are 0 and 1, which is different, the output is 1. When the input are 1 and 0, the output is also 1. Finally, when both inputs are 1, the output is 0. The Boolean expression for the XOR gate is written as y is equal to a XOR b. The plus sign inside a circle represents the logical exclusive or operation. The XNOR gate, which stands for exclusive NOR, is the inverse of XOR gate. Its output is high only when its inputs are same. Think of it as the logical same detector. The output is on only if both inputs are on or both are off. If the inputs are different, the output is off. The XNOR gate symbol looks like XOR gate with a small circle or inversion bubble at the output. The bubble signifies the logical inversion of the XOR gate. Look at the truth table. When both inputs are 0, the output is 1. When the inputs are 0 and 1, the output is 0. When the inputs are 1 and 0, the output is also 0. Finally, when both inputs are 1, the output is 1. The Boolean expression for an XOR gate is written as y equal to a XOR b bar or y is equal to a XOR b. The letter symbol represents the logical exclusive NOR operation. The universal logic gates, the NAND and NOR gates are considered universal gates because any other logic gates like AND or NOT can be implemented using only one of these types of gates. This property makes them very important in the design of complex digital circuits. Now that we know how individual logic gates work, let's analyze a simple circuit to see how they function together. We will trace the signal from the inputs all the way to the output. Let's start with the AND gate at the top. It has two input, that is A and B. According to diagram, input A is 1 and input B is 2. Note that the diagram labels input B with a 2 even though its logical value in the context would be a 1. Based on the AND gates function, it gives a high output only when both inputs are high. Since both A and B are logically 1, the output of the AND gate is also 1. The output of AND gate is represented by the Boolean expression A and B. The output of the first AND gate now becomes one of the input for the OR gate. The other input is C, which is a 3, but its logical value would be a 1. So the OR gate has two inputs, the output from the AND gate and the input from C. According to OR gate's rule, if either or both of its inputs are 1, the output is 1. Since both inputs of the OR gates are high, the final output is 1. The Boolean expression for this circuit is A and B whole plus C. The parenthesis shows that the AND operation is performed first and the result is then OR with the C. As we traced it, when A is 1, B is 1 and C is 1, the final input is 1, which matches the output shown in the diagram. Now, let's analyze a more complex logical circuit. Here we have four inputs A, B, C, D. It has three logic gates NOR gate, NAND gate, and a final OR gate. We will analyze this in the two steps. First, we will find the output of the two gates on the left, and then we will use those outputs as inputs for the final OR gate. Let's begin with the NOR gate. Its inputs are A and B, which are both logically 1 according to the diagram. A NOR gate's rule is that the output is only high if all of its inputs are low. Since A and B are both high, the output must be low. The Boolean expression for this part is A plus B bar. Now, let's look at the NAND gate. Its inputs are C and D, both logically 1. The NAND gates rule is that the output is only low when all of its inputs are high. Since C and D are both high, the output must be low. The Boolean expression for these parts is C and D bar. The two outputs we just found, a 0 from the NOR gate and 0 from the NAND gate, are now the inputs for the final OR gate. And OR gate's rule is that the output is high if any of the inputs are high. Since both the inputs are 0, the output is low. This gives us final output, which is 0. The complete Boolean expression for these entire circuits is A or B bar or with C and D or. You can see how we combine the individual gate expression to describe the entire circuit's functions. And that's our introduction to logic gates and basic gate circuits. You now understand the fundamental building blocks that power everything from your phone's processor to the memory in your computer. If you found this video helpful, please hit the like button and subscribe so you don't miss the part 3, where we will introduce Boolean algebra and K-maps, the powerful tools we use to design and simplify these circuits. Thanks for watching, and I will see you in the next video.